Hey everyone, it's Matt here from Kojo. So today we're going to be going over basic computer architecture. So again, it's going to be really simplified, but the purpose is because as we're going through iOS and Android development, we're going to be constantly talking about different parts of the hardware and different parts of the computer. So we just want to give you in one location what some of these concepts mean. So again, very simplified concept of a computer. We have three parts. We have the CPU, which is the central processing unit. This really is the brain. It's making all of the decisions. All of the logic happens here. RAM is also sometimes called main memory. RAM stands for random access memory. This is going to store our active running programs and data. It's called random access just because the CPU doesn't have to read everything in any kind of sequential order. It can grab some piece from over here and grab another piece from over there. So it can access things in some random order, whatever it wants to do. And then finally we have storage. So this is our hard drives, our USB, things like that. This is all of our inactive programs and inactive data. So a really good analogy I heard one time is storage is kind of like the file cabinet that you might have at an office or at your house. You're not actually using any of the data in there, but you know how to get to it. Once you actually want to use a file from there, you'd go and you'd open it up, you'd pull it out, and you'd lay it on your desktop. Now you can, whatever, fill out your taxes or things like that. So once it's on your physical desktop, we say that would be RAM. So obviously, if you had a larger desktop, you could actually be working on more files at one time. So the more RAM you have, it's kind of like the more programs or the more data you can actually work on at one time. So kind of a little bit more detail on the CPU. CPU has a couple of different parts. Again, you don't have to memorize all of this, but the control unit is kind of like the conductor. This is the actual brain of the computer. Actually, I don't want to say it's the brain. The conductor really is what it is. It's deciding when it reads an instruction, it decides what that instruction means. So it's decoding it, and it's looking at these two things, and it says, "Oh, do I need to add these? If that's the case, what type of data are they? I'll send them to the ALU." Or once we've added these numbers together, what am I doing with it now? Am I putting it back into a register? Am I sending it back out to RAM? Or am I sending it to the hard drive? Things like that. So the next piece is the ALU, which is the arithmetic logic unit. This is where all the math happens on integers or whole numbers. Originally, computers only had an ALU. They didn't have any hardware-specific piece for doing floating point math. And so that was fine for a lot of the times, although as computers started having graphical user interfaces, they wanted to have more input on, they wanted to be able to do math on floating point numbers. And so in order to make that faster, they started, you were able to buy a floating point unit as a separate chip, separate from your computer. These days, all CPUs just come with a floating point unit. But FPU does math on fractional numbers, so things like, 4.5. If you have a decimal place in the number, that math is going to be done on the FPU. Registers, you can see we have roughly less than 1,000 bytes. In general, we might have a couple of different register types, but a typical computer or typical CPU that we buy today is going to have about 10 what they call general purpose registers. These are registers that can hold code instructions and like the numbers that we actually want to do the math on, or possibly the memory addresses in RAM that we need to affect, that we need to move around. So the control unit can really only move things around and can only process things that are in registers. So for example, if we want to add two numbers together, it can't add two numbers from the cache, which we'll talk about. It can't add two numbers from RAM. First, the control unit will have to go fetch those numbers from RAM, put them in registers, and then send them to the ALU to do something with it. So everything that happens has to happen on registers or inside registers. And like I said, a typical CPU these days only has about 10 general purpose registers. So really we can only be dealing with 10 things at a time. The next piece that's on the CPU is the cache. And so you can see we have different levels of cache, and it can go anywhere from 512 kilobytes to about 16 megabytes. The purpose of this is to speed up fetching that data. So if the control unit reads an instruction that says I need to add these two numbers, it's first going to look to see, are these numbers already in the registers? If they're already in the registers, then it can just send them to the ALU and then do that math. If they're not, it's going to start looking out into the cache. So first it's going to see if it's in the L1 cache, and if it is, it will then bring it directly into the registers. If it's not in L2 or it's not in L1, it's going to look into L2, which is a larger subset of that memory. If it's not in, and then if it is in L2, it will then move that section into L1 and then back into registers, and so on. So if it's not in L2, it's going to do that same thing for L3. It's going to find out where it's at in L3, put that smaller subset into L2, put that smaller subset into L1, and then finally into registers. And if it's not in any of those, that's called a cache miss. It then has to go all the way out to RAM, which can take, we're going to see kind of some of the numbers, but it takes quite a bit longer. So it's going to go out to RAM, fetch as much as will fit in the L3 cache, so possibly up to 16 megabytes of RAM, put that in the L3, put that into L2, put that into L1, and then finally into registers. And so, like I said, the goal of having these different levels is to speed up process time, so it doesn't have to go and fetch from RAM all the time. So here's kind of an expanded view of RAM. Possibly we can have, I don't know, I guess we'll talk about what the exact limit is depending on if it's a 32 or 64-bit machine, but we can have gigabytes of RAM. At the lower addresses is going to be where the operating system is running, but then throughout the rest of RAM, we're just going to have our active running programs. And so a snapshot of what one of those programs might look like in RAM, we're going to have somewhere in there is going to be a section for code, somewhere is going to be a section for global variables, somewhere is going to be the rest of our data that we're actually currently working on. And so that's actually separated into two pieces called the heap and the stack, which we'll talk about. So code is all of the instructions and kind of any unchanging value. So it's the instructions like our functions on our classes, but also like if we just have the number 4 in our program, or if we just have some string called mat, then that's going to be stored in our kind of code and data section. These things never change. In a different section, we'll have what are called our global variables, and we'll talk about this in one of the programming, whichever programming language we're talking about, Kotlin or Java or Swift. We'll talk about exactly what global variables are, but this is some data that could change, but it's defined outside of any functions. So the lifetime of these pieces of data exist before the start of the program and after the program ends. So again, it exists for the lifetime of the entire program. The rest of our memory that the computer has given us, that the compiler has given us, is kind of distributed between the heap and the stack. And this is just where, these are just two different places where we can put our data. And you can see that these things do actually grow, right? So global data, global variables aren't going to grow because we know exactly how much we need right at the start of the program, right? Code isn't going to change because we're not adding code as the program is running. But the rest of the memory, we might be adding more and more pieces of data. So the stack, we we use that for all of our named variables inside functions. It might be function parameters as well. These stack variables only exist inside of a function, but as we call more and more functions, it's going to be growing, right? And then as we end these functions, it's going to be shrinking. So that's why I say it grows and shrinks based on these function calls. The heap is a little bit different. The heap is a little bit different. This is for dynamic variables, and depending on the language, a lot of variables might be dynamic. Again, we're going to talk about what exactly these things are, but the lifetime of these variables isn't tied to the lifetime of a function or the lifetime of the program. It's determined by us, the programmer, and really it's determined by the memory management strategy. And so that's why we're kind of going to talk about this. The stack versus the heap. This isn't something that you're going to be using every day, but as we talk more about memory management, like the garbage collection in Swift, or we talk about the automatic reference, I said that wrong, the garbage collection in Kotlin or automatic reference counting in Swift, eventually we're going to talk about how these things work. And really it's related to the difference between the stack and the heap. So the stack is, like I said, it's where the function calls, like as we're calling functions, as we're creating variables, the variables that we give names to are actually on the stack. So in C++, we might create some object called a foo pointer, right? Foo might only be 4 bytes. And so that 4 bytes is going to live on the stack, but the data for that foo would, because it's dynamic, is going to be created on the heap, right? And the reason these are separate is because things that are on the heap aren't affected by function calls. So that means that I can have a function allocate some data that I might need, like my player or something like that, or my current active user, and that user isn't tied to the lifetime of this function. So I can now exit out of this function and still use that user. Again, it's definitely confusing at the beginning, especially in languages like Swift and Kotlin, because actually there's not much that's happening on the stack and a lot that's happening on the heap. And we'll definitely talk more about that when we're talking about memory management, depending on the language that we're talking about. So here's some interesting characteristics of memory. So we kind of already talked about a lot of these, but registers, we have less than 1 kilobyte, and it's very, very, very fast to access these. We don't really have control over, we don't have much control over anything in here, but these registers are all managed by the compiler. The cache, again, there's different levels of cache, but we have around less than 16 megabytes, again, depending on which CPU that you buy. But you can see it can be almost as fast as accessing a register if it's in that L1, for example. But it could be up to maybe 50 times slower if it's not in any of those, or if it's not in the register. It could be 50 times slower to reach out to cache. We see RAM. We can have maybe around 64 gigabytes of RAM. Technically, we probably could have more, and we're going to talk about that. But I don't know any computers right now that have more than 64 gigabytes of RAM. But you can see it's going to be about, what is that? Worst case, it's like 10 times slower to access something from RAM as it is from the cache. And so if it's not in registers, what is that? So that is possibly 50 times slower, so 500 times slower to access something out of RAM if it's not already in registers. We also now have solid state drives. So these are faster hard drives, but we can see still accessing something from the hard drive, even our solid state fast hard drives, is just going to be very, very slow. And then the older style hard drives, magnetic disks, we can have terabytes and terabytes of these, but it can just be incredibly slow. So that's part of the reason why we're building, the computer manufacturers are building more and more memory on the CPU itself, so that the CPU acts much, much faster. And so, for example, if we're reading a number from a disk, so if we need to do some math, and that math is, and the numbers that we need to read are in some file that's on the hard drive, first we have to go all the way out to the hard drive, read that in. That's first going to go into RAM, which is where our active running program is, and then it's going to be pushed all the way down to the cache. So all of this right here, the cache and the registers, are all on the CPU. So it has to go first to L3, then, which is a larger subsection of your program, into L2, which is a smaller subset, into L1, which is an even smaller subset, and then finally into a register, and then you can do something with it. Okay. Again, as we see here, register, cache, RAM, this is actually all managed by the operating system and the hardware, so you don't actually deal with this at all, but it's good to understand these concepts, because it can get complicated, so I don't want to talk about it too much here, but it's just good to understand these concepts. Okay, so really quick, you might have also heard the concept of this is a 32-bit machine versus a 64-bit machine. I think Android just now deprecated 32-bit binaries. So now you have to build a 64-bit binary for your application. So what does the 32-bit versus 64-bit computer mean? There's actually a couple of different things that it means. And it depends on what we're talking about. But 64-bit CPU, this has to do with registers. Okay, so those registers that we saw on a 32-bit machine, they might only have 32-bit registers. Nowadays, they can have 64-bit registers. And so that is useful for a couple of different things. Obviously, 32-bit value is a lot smaller than a 64-bit value. And when we talk about binary, we're going to see these exact numbers. But that means that we can do math on larger numbers, if that's what we care about. But really more important than that is, because RAM is all just addresses, that means the register needs to know the address of a certain piece of data if it wants to actually pull that data from RAM. And so that's the other part that affects. It affects how many memory addresses our CPU can actually look at, basically, right? So what I mean by that is, if we have a 32-bit machine with a 32-bit register, it really can only, like, the highest value that it can hold is 2 to the 32 minus 1. So basically 4.2 billion different possible values, which equates to about 4 gigabytes of RAM. I kind of remember when I was younger, people were selling, like, you were able to buy like a free upgrade for a computer. Like, it might come with 4 gigabytes of RAM, and they would give you an extra 4 gigabytes of RAM. So for a total of 8 gigabytes of RAM, but on a 32-bit machine. Your machine actually won't run faster at all for that, right? But it was just maybe a good sales pitch. It just seems like it's a good thing to say more RAM equals faster computer, but in the case of a 32-bit machine, it didn't actually work that way. So for a 64-bit machine, we can hold, or the number of different addresses our CPU can actually look at is 2 to the 64 minus 1. So that's, I think with this many numbers, I think that's 18 quintillion. We call it, based on like gigabytes, megabytes, things like that, it's 18 exabytes. So we have A byte is 8 bits. Kilobyte is 1,000 bytes. Megabyte is 1,000 kilobytes. Then we go gigabytes, terabytes, petabytes, and exabytes, which is 1,000 petabytes, right? So we can address just an insane amount of addresses. We can have an insane amount of addresses. Like I said, right now, I haven't seen a computer that has more than, or at least like a normal computer that you can buy, I haven't seen more than, let's say, 64 gigabytes of RAM. But because we have 64-bit machines, we can expand it much, we can expand it, we can be expanding our RAM for a long time. We don't have to worry about that. The other thing that the 32-bit versus 64-bit might mean, or the thing that it impacts, is the bus size. So bus is just kind of like your like the wires, the data transfer. So that control unit needs to go out, needs to fetch data from RAM. But if it needs to do, let's say you have two 32-bit numbers, and the bus is only 32 bits wide, so it's going to take two fetches, right? You have to go and grab the first 32-bit number, and then go out and grab the second 32-bit number, and put those all into registers. If the bus size is bigger, if you have a 64-bit bus size, then you can grab both of those numbers in one single fetch. So this could be larger or smaller than the register size. I think I remember reading when computers first went from when computers first went from 16-bit to 32-bit, the bus size actually still hadn't changed, and the ALU hadn't changed. So even though you could have more RAM, which means you could be running more programs, the actual work that your computer was doing, it might still have to do double the number of fetches, right? The time it takes to do math on that 32-bit integer is still going to be double. So that's kind of what 32-bit versus 64-bit means. Different things like the PlayStation and the Xbox One, their bus size is like 256. The memory bus is 256-bit. And the reason it's bigger is so that it can grab more floating point numbers at one time. And there's video games are really focused on floating point numbers so that they can, let's see, how do I want to say it? Yeah, a lot of the math that goes into placing objects in 3D space is based on floating point numbers. And so things like PlayStation and Xbox, they're optimized to do a lot of these floating point numbers really, really fast. A lot of the floating point math, they're optimized to do it really, really fast. So they want to grab as much as possible at one single time. So that's kind of, again, that's like the basics of the difference between 32-bit and 64-bit. These days, I think everything's going away from 32-bit, so maybe it's just not that important, but it's reasonable to know. All right, I guess that's it. Let me know if you have any questions, and I'll see you in the next video.